When we find ways to connect all nodes in a network using the minimum length of edges possible, we're finding the shortest connection. Examples might include connecting sprinklers with the least or cheapest amount of piping possible, or connecting a business or school cabling for their intranet or electrical network. In this video, we'll look at what the shortest connection and minimum spanning trees are. We'll look at how we can find the minimum spanning tree. We will look at finding the minimum spanning tree using Prim's algorithm and Kruskal's algorithm. A shortest connection problem finds the most efficient way to connect a set of nodes. It involves finding the spanning tree of the shortest length, called a minimum spanning tree. Remember, a spanning tree is a set of edges that connects a network but has no circuits. This is an example of a spanning tree. It's connected and it has no circuits. When we set up sprinkler systems at home, generally there's only one point to connect to a tap. We can connect all the sprinklers directly to the tap. However, this wouldn't be an efficient use of materials. When connecting sprinklers, we don't need to connect every sprinkler directly to the water source. Usually, we would join the sprinklers together, like this. Remember, a shortest connection problem finds the most efficient way to connect a set of nodes. You might have noticed that both of these are spanning trees. When we solve a shortest connection problem, we find the spanning tree of the shortest length, called the minimum spanning tree. Prim's algorithm is one way to find the shortest connection or the minimum spanning tree of a network. The first step is to pick any node. The second step is to join this node to the nearest node. If two nodes are of equal distance away, choose one at random. Then we join the node which is nearest to either of those already connected. And we continue joining connected nodes to the nearest unconnected node until all nodes are connected. Let's look at an example. Find the shortest path or minimum spanning tree of this network using Prim's algorithm. We start with any node, let's say A. Join this node to the nearest node, which is B. If two nodes are equal distance away, choose one at random. They aren't in our example here. Now join the node which is nearest to either A or B, this is D. Continue joining connected nodes to the nearest unconnected node until all nodes are connected. The next closest node to A, B, and D is E, then G, now F, and C. And finally, we need to connect H. Now the whole network is connected with the minimum spanning tree. The minimum spanning tree in this example is 71 units. Let's quickly look at another example using Prim's algorithm. We can start at any node. I'll choose L this time. Join this node to the nearest node, which is G. Now join the node which is nearest to either G or L. There is more than one node that is equal distance away from G and L, so we'll choose one at random. I've chosen H. We'll continue connecting nodes to the set of connected nodes until all nodes are connected. M, D, K, I, F, E, A, B, C. Now we've found the shortest connection between all the nodes. The minimum spanning tree for this set of nodes is 21 units. Now let's look at Kruskal's algorithm. We choose edges one at a time, taking the shortest edge at every stage while ensuring that no circuits are formed. The first step is to choose the shortest edge. If there are several, choose one at random. The second step is to choose the shortest edge remaining that does not complete a circuit. If there is more than one possible choice, pick one at random. Then repeat step 2 until all the nodes are connected. Let's look at an example. The easiest way to use this algorithm is to create a table that includes all of the edges and their lengths in ascending order. I've done this already here. Start with the shortest edge. If there are several, choose one at random, choosing the shortest edge remaining that does not complete a circuit. If there's more than one, pick one at random. The first and shortest edge in this network is BD, which is 7. So we include it because it doesn't form a circuit. The next shortest is BE, which is 8. So we include it because it doesn't form a circuit. The next one is AB, and we include it because it doesn't form a circuit. And then we've got EG, and we include it because it doesn't form a circuit. The next one is CF. Note this does not need to be connected to the other nodes. The next one is DE. You'll notice if we connect DE, this will complete a circuit between BE and D, so we can't include it. We skip this one. The next one after that is FG. This doesn't form a circuit, so we include it. The next one is GH, and this doesn't form a circuit, so we include it. If we look at EF, which is 15, this will complete a circuit, so we don't include it. Now we've found the shortest connection between all the nodes. This is the minimum spanning tree, and it's 71 units. Let's look at another example. Again, I've created a table with all of the edges in ascending order. Start with the shortest edge, which is BC, and we include it because it doesn't form a circuit. And then we have AC, and we include it because it doesn't form a circuit. And then we've got CD, and we include it because it doesn't form a circuit. At this point, we can stop because we've connected all of the nodes and found the minimum spanning tree. The minimum spanning tree for this network is 770 units. So in summary, in this video, we've had a look at what the shortest connection is and minimum spanning tree. We've used Prim's algorithm and Kruskal's algorithm. Thank you.